Hello, welcome to Maths with EJD. This is the third video on eigenvalues and eigenvectors as far as numerical analysis is concerned. Do I have a more elaborate treatment of eigenvalues and eigenvectors under the first playlist on this channel that's talking about matrices. But here the focus is on numerical analysis. So our focus now is on numerical stability and condition numbers. So previously we had looked at introduction to eigenvalues and eigenvectors, and then later we saw how to use the power number method to calculate the dominant eigenvalue of a matrix whose eigenvalues may be difficult to compute. Okay, so let's go ahead and talk about this. Numerical stability refers to how errors in data or computations propagate through an algorithm. A numerically stable, I guess I want to go black here. A numerically stable algorithm produces small errors that do not significantly affect the final result. Okay. Conversely, an unstable algorithm amplifies errors, leading to inaccurate results. Okay. Um, understanding numerical stability is crucial in solving mathematical problems with limited precision, as most computations in practice are subject to rounding errors. All right, so now let's talk about condition number. That's numerical stability so far. So, we're talking about numerical stability and condition numbers. So talking about condition numbers now, we can say that the condition number, the condition number of a matrix is a measure of how sensitive the solution of a system of linear equations is to small changes or errors in the input data. Okay, a matrix with a low condition number implies that the solution is relatively insensitive to small perturbations, that is, small changes in values to small perturbations, while a high condition number indicates that small errors in the input can lead to large errors in the solution. Okay, so let's go back to talk about computation, right? Or to the definition of condition number. Condition number of a matrix. So the condition number A of a matrix A is defined as K of A equals norm of A multiplied by norm of A inverse as a condition number. So one, if K of A is large, the matrix is ill-conditioned. And solving the system can amplify errors. On the other hand, if K of A is close to 1, the matrix is well conditioned. And errors have minimal impact. Okay, so let's take a worked example. So consider the system of linear equations represented by AX equals B, where A is equal to 1.0001, and B is 2.0001, like this. So we want to analyze the numerical stability want to analyze the numerical stability of this system. Okay, so first thing to do is to compute, step one, compute the condition number. So the matrix A now, the matrix A is nearly singular, because if you look at it, a singular matrix, the determinant of a singular matrix is 0. So if you check the determinant, you discover that it's if not for the 1.0001, so 1 times 1, 1 minus 1 times 1, that's simply 0. So that's why the 1.001 is what makes it not to be totally singular, right? So the matrix A is nearly singular because the rows are very similar. The rows are very similar. So what we want to do is this. Let's compute the condition number using the 2-norm. So first, we need to find the singular values of A. The singular values are the square roots. They are the square roots of the eigenvalues of A transpose A. That's the transpose of A multiplied by A itself. So where A transpose A now, A transpose A is simply going to be, the original A is actually 1110. So A transpose A is 1, row 1, it becomes column 1, that's 1, 1. Column 1, row 2 becomes column 1, that's 1.0001. That's, in fact, it's a symmetric matrix because the original matrix is 1.0001. So if you transpose it to, so row 1 becomes column 1, then row 2 becomes column 2. So it's a symmetric matrix, interestingly. So that's what we have. So that's A transpose A. And of course, that's something like A transpose A is something like 2.0001, 2.0001. Then this is 2.0001, and this is 2.0002. That's an approximation actually, because it's longer than that if you check it out. So that's roughly what we have now. So then by computing the eigenvalues, we already know how to do eigenvalues, so I'm just going to write the eigenvalues out. By computing the eigenvalues of A transpose A, we have that lambda 1 is equal to 4.0004 and lambda 2 is 0.0002 or 5 or something close to that. So the singular values are the square roots of these eigenvalues. So, and these are simply, so the first one, the singular value 1 is square root of 4.0004, and that is approximately 2.0001. Then we have singular value 2, which is square root of 0.0002. That's approximately 0.0141, like that. Then we can then say that thus the condition, thus the condition number K of A is K of A, which is equal to sigma 1 all over sigma 2. And that is approximately 2.0001 divided by 0.0141, and that's approximately 141.5. Okay, that's really large. Okay, so this is a high condition number. This is a high condition number indicating and indicating that A is ill conditioned. A is ill conditioned. Okay, so let's look at some effects of perturbations on this situation. Effect of perturbations. That's like step 2 now, effect of perturbations. So we have computed the condition numbers and they're really high. I mean, the condition number is really high, that is. So we see that given that K of A is large, even a small error, in B will significantly, I want to squeeze that in. Yeah, I got it. Will significantly affect the solution X. Okay. For example, if B were perturbed by an error of tiny error, 10 raised to minus 5, that's 0.00005, 0.00001. So the error in the solution, X could be amplified by a factor of K of A, which is big, right? 141.5. So leading to much larger error in the solution. Now we talk about numerical instability. Numerical instability. You know, we're talking about condition number and numerical stability or something. Yeah, numerical stability and condition number, that's what we're talking about. So now let's talk about numerical instability. So in practice, due to the high condition number, solving AX equals B using direct methods. Remember direct methods like Gaussian elimination, LU decomposition, and Cholesky decomposition. Using direct methods would likely yield inaccurate results. Even direct methods that are guaranteed to give very good results, they are likely to yield inaccurate results due to amplification errors. Due to amplification of rounding errors, actually. Amplification of rounding errors. So that means the iterative techniques may be useful in this situation. All right, so as we come to an end of this, let's highlight some takeaways from here. So key takeaways now from this whole idea, key takeaways. So the first thing is that numerical stability, numerical stability ensures that small errors, small input errors don't drastically, don't drastically, don't drastically affect the result. That's one situation. And the next thing is that um, the condition number, the condition number measures how sensitive the solution, the solution is to changes in the input with a large condition number, with a large condition number indicating potential numerical instability, potential numerical instability. Okay. So just like we saw in the example, right, the high condition number suggests that the system is ill-conditioned and solving it would likely induce large errors in the solution due to the propagation of small errors. So with this, we come to the end of this video. For those who have subscribed, thank you so much. If you have not subscribed, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. Because from the next video, I'll be talking about some practical applications of eigenvalues and eigenvectors, and we have quite a lot of them, like principal component analysis, like image compression, and so on. I think I'll be talking about 5 or 6 of those in this next set of videos, applications of eigenvalues and eigenvectors. Then, of course, you want to comment, let me know how helpful these videos are, and also let me know if you have a topic you'd like me to teach or a problem you'd like me to solve. Of course, like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.